complex exponential and sinusoidal signals. Okay, let us start with a sinusoidal signal. Let's say cos omega naught t. What is omega naught here? Omega naught, what is it called? Sorry?
Angular.
It is called angular. Why is it called?
Angular.
Why is it called angular frequency? It is the angular frequency. And why is it called angular frequency? How is it related with complex exponential? Is it real part of e to the power j omega naught t?
Yes, sir.
Yes. Now you must have studied the phasor representation of these complex exponential signals. In the complex plane, we can represent this as a rotating phasor, isn't it? Is it? This is the complex plane. How can we represent this in a complex plane? For example, let us start with this. What is the value of the signal at t equals to 0? Where is that point?
So 1, 0.
It is at this point, isn't it? Now, if we take another time instant, let's say t is t1, where is that signal? Some point here. And what will be this angle?
Omega.
It is omega naught.
Omega naught t1.
It is omega naught t1. Now, if we sketch the values starting from 0, and if we are sketching that signal for all the values of t, then what about this length? This is 1, isn't it?
Yes.
So can we say that it is a phasor? Sorry, it is a phasor in the phasor rotating in which direction? Anti-clockwise direction. And what is the that rate of that is why it is called omega naught is called angular frequency, isn't it? What is the unit of omega naught? It is radians per second. Okay, so we can represent this complex exponential signal e to the power j omega naught t as a rotating phasor rotating in the anti-clockwise direction. Is it always in the anti-clockwise direction? Or it depends on the value of omega naught. If omega naught is greater than 0, it is rotating in the anti-clockwise direction, isn't it? If omega naught is less than 0, omega naught is less than 0. Is it a phasor rotating in the anti-clockwise direction? Clockwise direction?
Yes.
So it depends on the value of omega naught. So anyway, we can represent this complex exponential signal as a phasor in the complex plane, rotating phasor in the complex plane. And what is cos omega naught t? It is the real value. So this phasor is rotating. For example, if it is omega naught is greater than 0, it is rotating in the anti-clockwise direction with an angular frequency omega naught radians per second. Now, what is this cos omega naught t? Is it the projection onto the real axis?
Yes.
It is the projection onto the real axis, and projection onto the imaginary axis is sine. Okay. So this is the phasor representation of complex exponential signal e to the power j omega naught t. Now tell me, this e to the power j omega naught t, is it a periodic signal?
Yes, sir.
Always periodic?
Yes, sir.
It is always periodic because when t is 0, the phasor is starting from here. So after some time, it will reach here, isn't it? Whatever be the angular frequency, it will reach here. Now, what is the fundamental period of that signal?
2 pi by omega.
It is 2 pi by omega naught. Since we consider the fundamental period of a signal as positive, we consider the absolute value, because if the signal is rotating in this direction also, like let's say this is 2 pi pi radians per second, it is rotating in the anti-clockwise direction. So its fundamental, what is the fundamental period? In this case, if omega naught is pi, then it is 2. T naught is 2, isn't it? 2 seconds. Now, what is the fundamental period if it is minus pi radians per second? Minus pi radians means it is rotating in the anti-clockwise direction with the same angular frequency. So there also the time period is the same, isn't it? We define this time period as a positive quantity, fundamental period. That's why we are taking mod here. So this is the fundamental period of the signal. Okay, so if the complex exponential is periodic, then its real and imaginary parts are always periodic, isn't it? Sine and cosine signals. Now let us consider. So what is the phasor representation of this? Phasor representation of this? Is it somehow related to this phasor representation that we discussed earlier?
Yes, sir.
What is the difference?
It at time 0 it starts with start of pi radians.
So at when t is equal to 0, here the phasor is here, at this point. Now when t is 0, the phase angle is not 0, it is. So this is the point. Okay. Now it starts rotating in the anti-clockwise direction with an angular frequency omega naught radians per second, isn't it? So initially we say that there is a phase shift. This is called phase shift. Why is it called phase shift? Because this is called the instantaneous phase of that that rotating phasor. So there is a phase shift, this phi. Now what about the periodicity of the signal? E to the power j omega naught t plus phi. Is it a periodic signal?
Yes.
It is a period. It is a periodic signal. It is is it same as the previous one without phase shift?
Yes, sir.
So it is same, isn't it? So can we say that this phase shift that won't affect the periodicity of that signal, is it?
Yes.
Excuse me, sir.
Yes.
Sir, we are saying that this function is periodic, so we should take t negative also.
T negative, which T?
Omega
No,
naught
no,
t
it's okay.
t should be
It's
having all
it's
over.
okay. That's what I am saying. T negative means, what is the meaning of negative time? We are considering some reference time. That is we are taking as T0. Okay. So the phasor is, if we consider the negative period, the phasor is not starting from here. It is rotating, and at time t equals to 0, it is reaching here. That is our assumption. Okay, sorry, this is without phase shift. And if there is a phase shift, it is rotating, and at time t equals to 0, it reaches this point.
Yes.
Okay. So this is always, this is an important point. This is called the phase shift, when we calculate the fundamental period of that signal, we can neglect this phase shift. Okay. Now let us consider this cos omega naught t without phase shift. This is a cosine signal. Okay. So this is without phase shift, because at t is equal to 0, this is 1. Now with phase shift, what will happen? What is this cos omega naught t plus phi? If there is a phase shift of phi, what happens to this signal?
Shift toward right or left.
Right or left, depending on what?
Phi.
Depending on phi. So if
Sign of phi.
yeah, it is
Positive
yeah,
or
if it is positive, shifting left or right?
Left.
If it is positive, shifting left, isn't it? It is time advance, isn't it? Because if there is no phase shift, we are starting from here, and it takes some time to reach here. And if there is a phase shift, we are starting from here. And how much time it takes to reach here? This phasor. If without phase shift, we are starting from here, how much time?
So 5 by omega naught.
It is 5 by omega naught. So can we say that this signal, cosine signal with a phase shift, that is a shifted version, shifted left, and this difference, this and this is how much? 5 by omega naught. Is it that? It is 5 by omega naught. That is time shift. So can we say that the phase shift is effectively a time shift in this case?
Yes, sir.
And we can derive it from this here also, cos omega naught t plus phi. We can write this as cos omega naught into t plus phi by omega naught. Okay. So from here to here, if we are starting with a signal cos omega naught t without any phase shift, how to get this signal? What is that operation?
So time shifting.
We are replacing t with t plus phi by omega naught. That is time advance by phi by omega naught, isn't it? It is time shifting. Is it? Okay, so that's about continuous time, complex exponential and sinusoidal signal. Here, okay, let me explain few more things. One is here cos omega naught t plus phi, that is equal to cos omega naught t plus phi by omega naught. Meaning is that it is equivalent to a time shift. So we can say that phase shift implies time shift. Okay. Now, what about time shift? Does it imply phase shift? If we have a signal cos omega naught t, we are shifting the signal by t naught. So this is cos omega naught t plus omega naught t naught, isn't it? Is it? This is, we are shifting the signal. This is time shift. It is equivalent to what?
Phase shift.
Equivalent to phase shift. Okay. So that is true for continuous time signal. Now let us consider discrete time signal, discrete time complex exponential and sinusoidal signals. Let's say cos omega naught 10. Let us consider an example. Let's say omega naught is pi by 2. So what is omega naught here? What is the unit of omega naught? First, let us see what is the phasor representation of this. What is the phasor representation of e to the power j omega naught n? When n is 0, where is that the value that value of the signal? Is it here? This point.
Yes.
This at n when n is 0. Now when n is 1,
Cos omega.
is it this? And here and is it that? So here omega naught is radians per sample. Okay, its unit is radians per sample, and most of the times we consider this n as a dimensionless quantity, and so it is generally we express omega naught as in radians only. Okay, it is generally we don't say radians per sample, it is radians. Now the question is it a periodic signal? Discrete time complex exponential signal? What is periodic signal? Let's say this is n, when n is 0, the value of the signal is this. This is for 1, 2, 3, 4. Is it that pattern repeating?
Yes, sir.
So what is this? Is a periodic signal. What is the fundamental period of that signal? This particular signal?
4.
This is 4. It is a periodic signal with period 4. Okay, now let us consider another example. Omega naught is 3 pi by 2. Where is the first value is here? Where is the second value? This is pi plus pi by 2. So this is 1. Where is the third value? Again, this is pi plus pi by 2. And then, sorry, let us start with 0. This is 1, 2, and this is 3. Is it that? Is it a periodic signal? Is it a periodic signal?
Yes.
Yes,
It
sir.
is a periodic signal. If we are starting from here, after some samples, if we reach here, it is a periodic signal. In this case, it is happening. This is 4 is the fundamental period. Now, can you tell me, is there any difference between these two signals?
So rotating in opposite direction.
Rotating in opposite direction. We are starting with this is 0,
Sir,
1,
image about
2, 3. Its rotation is always in the anti-clockwise direction if omega naught is positive.
sir, image about the real axis.
No, it is not image about real axis or anything. How many rotations are there in one period here? In this example, we are starting from here. This is the first, this is 0, 1, 2, 3, 4. So after one rotation of the phasor, it is back to this point, isn't it? Now, what about this? How many rotations? Starting from here, 1. So it is crossing once, 2, How,
4 rotations.
4 rotations or 3 rotations? It is 3 complete rotations, isn't it? It is 3 rotations, not 4 rotations. But it is periodic. Now, what about a continuous time exponential signal? We are starting a phasor from here. After one cycle, it always reaches here, isn't it? That same point. But here, it may take more than one cycles. Now, is it always a periodic signal, discrete time signal? Discrete time complex exponential signal, is it always periodic?
No, sir.
No. What is the condition?
Let's say if omega naught is not something times pi, then
Something times
it
or
may not be
what something times? It is a rational multiple of pi, isn't it?
rational.
Rational
Yes, sir.
multiple of
If it
pi.
is not of that form, then it might not be periodic.
Not it. It is not. Might not be. It is not periodic then. So what we can easily verify that if we are starting from this point and this is said to be periodic if after some samples if it reaches here, isn't it? If we are starting from here, after some samples it should reach here, the same point. Then we can say that it is a periodic signal. And it may take, we have seen that in the case of discrete time signal, it may take more than one rotation. Now, can we say that if it reaches here, the angle is 2 pi, but it's the same? It is the number of rotations. Is it that? Now, what is the condition for this signal to be periodic? If it is periodic with some period n, what is that condition? Is it this? Because each sample, what is the extended, the angle between these two phases? It is omega naught, isn't it? So omega naught into n, that must be equal to 2 pi m. Then we can say that the signal is periodic. And we can say that 2 pi is, omega naught is, this is the condition. Is it that? Here m is an integer. It is an integer multiple because complete cycle means it is an integer multiple of 2 pi. So m is an integer. Since it is a sorry, can you please mute the microphone? So is it the condition for that signal to be periodic if e to the power j omega naught n, if this is periodic, then this condition must be satisfied, isn't it? And what is the fundamental period?
4.
In this case, it is 4. So can we say that if it is e to the power j omega n, so it is 2 pi m by omega naught. Again, let's take it as mod omega naught. So can we say that the fundamental period of this signal is this value for which one? Minimum value of m, isn't it? Is it? Is it the fundamental period? And that minimum value of n corresponds to what? It is the number of rotations, number of complete cycles in one period, isn't it? So this is the condition. If omega naught is a rational multiple of pi, then it is periodic. For example, if you consider e to the power, let's say e to the power j2n, is it a periodic signal? It is not a periodic signal. Okay, so that is a difference between continuous time complex exponential and discrete time complex exponential. Continuous time complex exponential is always periodic, but discrete time complex exponential is periodic only if this condition is satisfied. And another difference is here the value of omega naught is different, isn't it? Here it is pi by 2, 3 pi by 2. But what is the fundamental period of the signal? Is it 4? And what about the fundamental period of this? What is the fundamental period of the signal? E to the power j 3 pi by 2n. It is also 4, isn't it?
4/3.
4 by 3, fundamental period. We are talking about a discrete time signal. Okay. So it is not 4 by 3. The fundamental period is 4. That means after fourth sample, that pattern repeats. It is starting from here. This is 1. Second sample. Third sample. 0. This is 1, 2, 3. And the fifth sample is this one. So it is period. The difference that is periodic with period 4. It is not 4 by 3. So here, in this case, omega naught is different, but the fundamental period is same. Now, what about a continuous time signal? If omega naught is different, then T naught will also be different? Yes or no? In the case of a continuous time signal, if we are starting from here, after one rotation, we will reach here. So if we increase the value of omega naught, what will happen to T naught?
Decrease.
Always decreases, isn't it? But that is not the case in the for discrete time signal. Okay. Do we have? Okay, let us discuss about this phase shift also. E to the power j pi by 2n plus pi by 4. What is the phasor representation of this? Where is it? Where is that point? Where is that phasor when n is 0? Is it this? At this point? Actually, it is a phasor rotating in this. Oh, sorry. This is when. And what is this angle? This is pi by 4. So the meaning of this phase shift is that if there is no phase shift, we will start from here. This corresponds to n equals to 0. And if there is a phase shift, we are starting from here. What about the fundamental period? Is it a periodic signal?
Yes, sir.
It is a periodic signal. Only we can say that only thing is that it is rotated. It is rotating by pi by 4 all the sample points. Is it that?
Yes.
Okay. Now, how is it related with e to the power j pi by 2n? That means without any phase shift.
Same fundamental period.
No, signal, earlier we have seen that in the case of continuous time signal, if there is a phase shift, we can get the same signal by time shifting, isn't it? Is it possible here?
Scaling.
Scaling, what scaling? Suppose if we are taking, if we consider this without phase shift, these are the sample points, isn't it? These are the sample points without, this is 0 and 0, 1, 2, 3, 4. Okay. Now, if there is a phase shift of pi by 4, this one is 0. Here it is, this one is 1. My question is, can we get this signal by shifting this sequence? Is it possible?
So it's like phase is integral multiple of omega naught.
No, I am talking about this particular. I am talking about this particular signal. Let us sketch that signal. If there is no phase shift, the first value. Let us consider cos pi by 2n. Okay, cos pi by 2n. So that means there is no phase shift. First value is here. This one, actually there is a cosine signal and we are sampling that some values of that cosine signal, isn't it? This is the first value, this is the second sample, and this is the third one, fourth. Okay. Now if there is a phase shift of pi by 4, this one, isn't it? The first value is this one. So there is a shift like this. Now my question is, can we get this sequence by shifting this? The form of complex exponential signal that we discussed in the previous class is this, e to the power j omega naught t. Okay, this is a complex exponential signal, but this is a special case of a complex exponential signal. The general form of a complex exponential signal is e to the power j, sorry, e to the power sigma plus j omega t. Okay, you must have studied this in your mathematics course, Laplace transform. Laplace transform, you express it in terms of e to the power st, isn't it? Have you studied Laplace transform in your mathematics course?
Yes, sir.
So this is the form, isn't it? E to the power st. Here s is a complex variable sigma plus j omega, where sigma is the, sorry, this is, sigma is the real part of s and omega is the imaginary part, isn't it? Anyway, we'll discuss about this Laplace transform in detail later, probably after the midterm. So here, this is the general form of a complex exponential signal. Now, can you tell me what is the shape of the signal e to the power j sigma, e to the power sigma plus j omega. Let us consider the real part of this, because this is a complex valued function of t. So if we want to sketch it, we have to take the real and imaginary part. Let's consider the real part. So can you tell me what is the shape of the signal, real part of the signal? Will it depend on the value of sigma? Let us say sigma is less than 0. Then what will be the shape of the signal? Real part of it is
Decreasing.
it is, let's say the amplitude is, so this will be the signal. It is a cosine signal with exponentially decaying amplitude, isn't it? Amplitude of that signal decays exponentially, and if sigma greater than 0, then it will be a growing exponential. The amplitude grows exponentially. So this is called a damped sinusoid. You must have studied this in your circuit theory course. If you have not studied, you will study this. So this is a general form of this is the general form of a complex exponential signal, and e to the power j omega t pure sinusoid. This is a special case of this when sigma is 0. Okay.